Okay, we're off to the races, and this is our final example of benzenes. Can you believe it? It seems like we've been talking about benzenes for a whole month, and we probably have. So with this example problem, it says, what's the major product for each of the following reactions? And A is bromination of p-methyl benzoic acid. I'm sorry. If you can't draw me the structure of p-methyl benzoic acid, give it up now, because you're not going to be able to draw me the product of that reaction with p-methyl benzoic acid. They're not going to give you the structure. I'm not going to give you the structure. If you cannot use the rules of nomenclature with benzenes and substituted benzenes, you're not going to be able to answer these problems. Again, it's a foundational course. You got to learn the basics before you go further. And here is proof in the pudding of why that's so important. All right, so we're going to start with methyl benzoic acid, but it's in a para position. Okay, so here's my benzene. The P means para, so they're directly opposite of each other. And I have a methyl, and I have a benzoic acid, a C double bond O with an OH. Okay, now what if you flip these around? What if you wrote the C double bond OOH up at the top and the CH3 down at the bottom? It's okay. It's the same structure, folks. It's the same thing. There's no difference. That's just the way that it was written, so that's the way I'm going to write it down. And what we want to do is that we want to brominate it. So we're going to add in Br2 with FeBr3. We want to know where this goes. Okay, so I take a look at these two things. Here's a methyl group. Methyl group is an activator. Methyl group is a ortho para director, but I can't do para because something's already there. So these two carbons, ding, have been identified. Site of location, I'm directing incoming traffic. Bromine, this is where you're going to have to land. All right, well, this does the same thing. It's a deactivator, but it doesn't mean anything right now. We'll worry with that when that time comes. So this is a deactivator on the chart. The deactivator is meta. So that meta position is meta to that group. All right, so here's OMP, Becky. There's the meta. So here and here. Folks, these are in agreement. The methyl group and the carboxylic acid group are basically telling the bromine to go to the same spot. They are not competing against each other. So my CH3 is going to stay here, and then my C double bond OOH will stay down here, and either to the left or to the right, it doesn't matter, that is where my bromine is going to go. Simple, clean, easy. There you go. That's it. So now I have a tri-substituted benzene as a product. Okay, so the next one is a benzene, and it says ortho of each other. All right, so I got a group here and maybe a group there. And it's orthobenzene dicarboxylic acid. Woo! Okay, so C double bond OOH and then C double bond OOH. Ortho, benzene, di, meaning two, carboxylic acid. So we want to chlorinate this. All right, so that means my Cl2 is going to come in with FeCl3. What kind of product is going to get formed? Okay. Well, these two groups are the same. We'll talk about both of them at the same time. Both of these are deactivators. Deactivators are metas. OMP, Becky. There's a meta. OMP, Becky. There's a meta. All right, well, that's to the first one. That's to this carbon. Okay, so that means this carbon, which is the site of attachment, there's the M, and there's the M location. Okay, so if we have this orthobenzene dicarboxylic acid, and I go back and I take a look at this other carboxylic acid. Now we're talking about this one. It's meta to that carbon. OM here. OM here. Oh, goodness gracious. So, two carboxylic acids side by side. Because of their locations and because they're both meta directors, every freaking carbon in the ring is a target. We don't like that. Okay, so one's going to outweigh the other, right? Not in this case. And the reason that it doesn't happen in this case is because they're the same group. One is not going to outweigh the other. So that means I'm going to have to write down these possibilities. So here's my benzene ring. Here's my COOH group. Here is a COOH group. And I'm going to add on my chlorine. All right, so my chlorine could go here. There's my first possibility. All right, so I'm going to do this again. Here's a COOH. There's a COOH. And now my chlorine could go there. There's a possibility. All right, so then I'm going to do this again. My COOH, my COOH. And then I'm going to put my chlorine here. No. Because that's the same as option number 1. That's the same. Carboxylic acid, chlorine. Carboxylic acid, chlorine. Okay, so that's not a different product. I've just got to be careful with that. It's not a different product. Okay, well, what about here? I'll put my chlorine there. Okay, well, are these two the same? Carboxylic, skip, chlorine. Carboxylic, skip, chlorine. Folks, if you had to name these, those are also identical. So that's not really a different product either. Just don't fall for the trap. That's what they wanted you to do with this one. They wanted you to write down an answer that included a chlorine here and a chlorine there and a chlorine here and a chlorine there. And if you do that, that's wrong. Because you get duplicate types of molecules that form. You just got to be careful of where they're located. And again, that's all due to the name. If you can name them the same way, then they are the same structure in the end. All right, so there's the answer to B. Now let's take a look at C. C gives me a benzene ring, and this is a chlorobenzoic acid, but it's para. All right, so there's chloro, and then here is a COOH, which is, again, C double bond O and an OH group. That's what that is. Okay, chlorine is a weakly deactivator, but it's ortho-para. All right, so ortho and ortho, para doesn't count. Something's already there. The carboxylic acid piece, that is at the bottom of the chart. It's a deactivator. It's meta. All right, so meta means it will go here and it will go there. That's meta to the carboxylic acid. So that means if we brominate it, these two things are in agreement. Because they are in agreement, we will get one product, pretty much it. My chlorine, my COOH, and then off of one of these carbons that have been identified, I get a bromine that happens there. All right, D. D tells me I have a benzene ring. The benzene is P of each other, so one here and one there. And the P location has a fluoro in it, so F. And then it gives me the word anisole. Oh, goodness. Do you remember what the anisole structure was? I hope. It was one of those that you should have remembered. It's an O CH3 group. So we need to take this molecule and we need to nitrate it. All right, so I'm going to add HNO3 and H2SO4. It's great. Okay, so I look at my fluoro group. I do what I've done before in all the others. There's no difference. I look at my fluoro group and I say, hey, weakly deactivator, but it's an OP director, so there's an O and there's an O and P is taken. And then I look at the OCH3 group. And the OCH3 group, that oxygen has free pairs. Those free pairs can get donated to that ring. It can participate in delocalization. Therefore, it is an activator, and all deactivators are OP directors. I didn't even need a chart for that. So those locations are going to be O of the methoxy group and para of the methoxy group. So we've got 4 competing sites of location. They're not in agreement. You're going to get different stories depending on who you go to. It's real life as well. So who outdoes the other one? Is there one? Sometimes they're not. We've already talked about that. But in this case, there is. Because if I look at the chart, the OCH3 group is a stronger activator than the F. It's above it in that chart. And because it's a stronger activator, that is going to call the shots. And that's going to make this molecule, when it decides to react, to say, okay, here's the F, here's the OCH3 group, that wears the pants, that's calling the shots, which means that ortho or para of it, that is where the NO2 group is going to go. It can't go para, fluorine's already there. So you pick either left or right, it doesn't matter, and you slap on an NO2 on one of those sides. That's all you got to do. And there's the product for that question. A tri-substituted benzene right there. Okay. Also, never forget that some of these I can ask you to name. How would we do that? Okay, well, here's the benzene with the OCH3 group on it. I can use the term anisole in order to name that entire piece at once. By default, that makes that carbon number 1. So at carbon number 2, I have a nitro, and then at carbon number 4, I have a fluoro. So F comes before N. So 4 fluoro, 2 nitro, anisole is going to be the name of that product. Again, it's a very quick review of everything that we've learned up to this point, right? We're talking about benzene. We're talking about reactions of benzene. We're talking about common names with benzene. We're talking about substituted groups on the benzene. We're talking about activators. We're talking about deactivators. We're talking about OP directors. And we're talking about M directors. Folks, it's all wrapped up into one example problem. What better question to ask if I really wanted you to kind of prove to me that you knew what the benzene reactions were all about? Right here is one of those questions. Everything that we've studied at this point is represented in that one little bitty simple example problem. All right, E. E is going to give me a benzene, and this is para of each other again, so para directly across. On one of these spots is a methoxy. So methoxy is meth and an oxy. So this is an OCH3 group. And then the next one is benzaldehyde. So benzaldehyde is an aldehyde group. So C double bond OH. All right, so let's identify these. With the methoxy, this is an activator. That activator is an OP director. All right, so O's, P is taken. And then I go to the aldehyde piece. The aldehyde piece is at the bottom of the chart. That's a meta director. So meta, meta. They are in agreement here. And what we're doing is we're nitrating yet again in the example problem. All right, so here's the nitration. And there's my benzene ring. My OCH3 group does not get attacked. My C double bond OH group, nothing changes to it. And your pick, either left or right, it doesn't matter. And you're going to add on an NO2 at that spot. Folks, there's your answer to E. All right. Now we do F, which is the last one and the last example of the video series for this grouping of benzenes. So here we have a benzene, and it tells me P, okay, there it is, tert-butyl methyl benzene. Oh my goodness, what? The nitration of P, tert-butyl methyl benzene. Okay, that's not a problem. Breathe. Right? Tert-butyl. Okay, butyl means 4, and it needs to be a tertiary carbon on that group. There you go. That's what that is. Tert-butyl. 1, 2, 3, 4 in total. Tertiary. Because there's a tertiary carbon in the middle. Now, of course, it doesn't count that one to the benzene. This is tertiary to the 3 around it. And then the other one's methyl group. There's the methyl. So we want to nitrate this thing. Okay, so that means I need to add HNO3 and H2SO4. Do them just like you did before. Both of these are R groups, so therefore we'll talk about them at the same time. The one on top is an R group. It's an alkyl group. The one at the bottom is an R group. It's an alkyl group. Both of these have the same thing going for them. Both of these are activators. Both of these are OP directors. In each case, the para positions are taken from each other. So para is not going to work. So the tert-butyl, this carbon right here, it's ortho-para to that carbon. So this one's going to work and this one's going to work, but the para will not. This carbon down here at the bottom, this methyl group is an R group. It's an OP. It's an OP to that carbon. So ortho's going to work, but para will not. So we get ding, 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 all 4 of these to register. They are not in agreement. At the same time, they stand equal footing. The reason for that is they're both R groups. One does not outweigh the other. So what does that mean to you? Well, here is the tert-butyl group, and here is the methyl group. All 4 of these are targets for that incoming NO2 group. So you put it to the left or to the right, it doesn't matter. Either one of those are okay. Plus, here's my tert-butyl group at the top. There's my methyl group at the bottom. And then here is an NO2 group, and you put it to the left or you put it to the right, it doesn't matter. But you do not put them on around. And the reason is that if you put it here, that's the same as this one. And if you put it here, that's the same as the first one that you did. It's just on the other side. It's still ortho to that group. It's still ortho to the group down below. So you do not get 4 different products here. And that's because 2 of them are repeats. It's just on the other side of the ring. So you got to keep that in mind. All right, so there is the story with tri-substituted benzenes and making those tri-substituted benzenes. Groups will outweigh one another. Groups will be their own directors. Sometimes they're in agreement and sometimes they're not. It just really depends on what groups are present and where they're located on the ring structure. All right, so one of the things that I do want to do, though, is I want to talk about other ways to break that carbon double bond O that we have been seeing in these reaction schemes. You know, we always add it like H2 and platinum, right? And we said H2 and platinum will break the C double bond O, and it will destroy that into just a straight carbon chain. We took advantage of that in a couple of our example problems that we saw. H2 platinum, H2 palladium, whatever the case was. I told you it really didn't matter. There's two other ways to do this, though. And one is called the Clemmensen reduction, and the other one is called the Wolff-Kishner reduction. I want to introduce it now, and the reason is because you'll see this in detail much later. So I want to kind of tell you, listen, what we've talked about in this lecture, it will kind of creep up again a little bit later on in the carbonyls. And this is where those two reactions are going to be introduced. The Clemmensen and the Wolff-Kishner is going to be introduced in the carbonyl reaction family. And that's our next set of lecture modules that we're going to be focused on. So the Clemmensen uses zinc and hydrochloric acid. The Wolff-Kishner uses what we call hydrazine in order to break that double bond O, and both of these are possibilities. So if you are reading in the text and you're flipping through some of these example problems in the benzene reaction, you might see them kick around these two terms, or you might see them use these types of reagents. And that's why they're doing that, because they assume that we've already talked about carbonyls and we haven't. As you can see, we've never really had to use them, except for one time. And that one time we said, hey, listen, if you can't fix it with H2 platinum, we've got another option for you, and here's the other option. That's it. So it wasn't a big deal that we skipped around the way that we did. But Wolff-Kishner and Clemmensen can show up in the benzene chapter. And if you are reading through this, that is one of the reasons that they're doing that. All right? Okay, so with that said, that's it, folks. No more. So this is it of this entire benzene reaction. No more benzenes, at least for a little bit. That's it. There's going to be no more. Go home. Enjoy the show. And good luck on the online assignments. Good luck on the upcoming test. I think that it will be a review of the test that you had previously, because benzene was represented on that one. And now you're seeing that benzene will be represented on the next one as well. All right, so that's it. Congratulations. You survived another lecture module. And until the next one, folks, take a break. I'm sure that your mind is throbbing at this point. But again, that's organic. Good luck.